Hello, my name is Seth Holder. This is our Physics 1 Lab 2 on projectile motion. In this lab, we recorded a video and imported it to Tracker where we tossed a ball in a upward motion and recorded its position at various times. And then we inserted that into GlowScript where we could code and see the forces acting on the ball. We made 3 graphs, one with our original data from Tracker where we calculated it, 2 a force where only the force of gravity was acting on the ball, and 3 a force in GlowScript where both gravity and air resistance or drag were acting on the ball. Fundamental principles and models that we used during the lab. We used Newton's second law, which calculates the acceleration of an object depending on its mass and the amount of force applied. We used the velocity update formula, the position update formula, and the force of gravity and drag. This is just an overview of what we did in Tracker. We took a video tossing the paper ball. We tossed it from about 1 meter high. The time step between each calculation is 0.033 seconds. It created a time, x-axis, and y-axis graph, but we only used the time and y-axis. And each tracking location was done by hand. These are some assumptions we made for our computations in GlowScript. We assumed gravity and drag are the only 2 forces acting on the system. We assumed that all tracker markings were placed at the center of the ball. We assumed that the x-axis speed was constant throughout the whole time the ball was falling. And we assumed the ball was a system and everything else was the surroundings acting on it. These are some of the GlowScript code's initial conditions. We weighed the ball to get the ball's original mass. We chose 2 points, subtracted them, and then divided by delta t so we could get the ball's velocity, like its initial velocity vector. For drag force, although it is shown on the screen, this is not the drag force which was used for the calculations. On the next slide, you'll be able to see that I once again put it in the loop, and so this is because the drag force would change at each consecutive time step as the velocity of the paper ball was changing. And so I just decided not to use this, but it is there to give me an idea of what I needed to do for the next slide. As I just mentioned, you can see here how the drag force is calculated again before we ever calculate our Fnet. We then use our position update formulas and velocity update formulas, as the ball velocity is equal to the velocity plus the Fnet divided by mass times delta t, and the position is equal to the ball position plus the velocity times delta t. And this is just so we can accurately calculate the position of the ball at each time step. And we did time steps of 0.001 seconds to make sure they were small enough to be super accurate. As we can see here in our analysis of results, we have our base tracker data graphed along with our 2 computational models. The base one is shown in green, and we plotted each of our points found in Tracker. The orange one is the one where we only calculated the force of gravity acting on the ball, and the blue one is the one where we calculated the force of both gravity and drag. As we could see that over a short time interval, there's not much deviation between the results, but as more time passed, there is a larger deviation between each of the results. Any differences between the drag force calculated with the computer and our base tracker results are probably due to human error, as we could have calculated the drag force slightly wrong, and we could have not plotted the center of the ball in Tracker, leading to slight differences in the data. Here, there is terminal velocity happening in the drag force data. This is because terminal velocity is where the net force is 0, and you need the air resistance or the drag force to counteract the force of gravity. And so we could see that as time passed near the end of our graph, it was starting to level out. This is where it was approaching terminal velocity. The question was, what if the ball was thrown straight up instead of at an angle with the same speed? Would it take longer to reach the ground? The answer I got for this is yes, because our initial velocity had 2 different directions, and as I explained earlier, we chose 2 points and subtracted Ri from Rf, and then divided by delta t. If it was thrown straight upwards, it would just be the magnitude of this speed, which would make our new initial velocity, as seen here, 1.869, which is much faster, and the force of gravity would have to counteract more than it did in the original system.